Welcome to our exploration of time dilation, a fascinating concept in physics that shows how time is not as constant as we might think. Time dilation challenges the ordinary perception we have of time, revealing that it can stretch and compress depending on various factors. But why is this important? In the realm of physics, understanding time dilation is crucial. It plays a key role in the theories of relativity and affects the way we perceive motion and gravity. Throughout this video, we'll uncover the science behind time dilation and its profound implications on our understanding of the universe. From Einstein's groundbreaking theories to real-world examples, we'll break down this complex topic into digestible parts. Join us as we delve into the intricacies of time dilation and embark on a journey through space, time, and beyond. You'll see why time dilation is more than just a theoretical concept, it's a fundamental aspect of how the universe operates. We often take time for granted, thinking it ticks away at a constant, steady pace. Our days are filled with routines, each governed by the relentless march of the clock. But what if time isn't as stable as we believe? What if time can stretch and compress, warping under certain conditions? Imagine a world where time flows differently depending on how you move or where you are in the universe. The idea seems like a sci-fi fantasy, yet it's a fundamental truth in the realm of physics. Understanding time's true nature challenges everything we think we know about reality and our place within it. In this video, we will unravel the mysteries of time dilation, showing you how time's fluidity impacts our universe in profound ways. You'll see how this fascinating phenomenon was uncovered and what it means for us all. Welcome back to our journey through the mysteries of time. In this segment, we're diving into Einstein's revolutionary theory of relativity. For centuries, time was thought to be constant, a fixed backdrop against which events unfolded. But Einstein shattered this idea, revealing a much more fluid and dynamic reality. His theory of relativity fundamentally altered our understanding of space and time, intertwining them into a single, four-dimensional fabric known as spacetime. One profound implication is that time is not absolute, it can stretch and contract depending on speed and gravity's influence. Imagine two clocks, one on a speeding train and the other stationary at the platform. According to Einstein, the clock on the train ticks more slowly than the one on the platform. This phenomenon, known as time dilation, is a direct consequence of his theory. It's a mind-bending concept that defies our everyday experiences. At high speeds, close to the speed of light, time begins to behave differently. Einstein's equations show that the faster you move, the slower time passes for you compared to someone stationary. This means that astronauts traveling at high velocities would age more slowly than those of us remaining on Earth. Einstein's insight didn't just stop at motion. Gravity, too, plays a crucial role in how we perceive time. Near massive objects like planets or stars, time noticeably slows down. This effect has been confirmed through experiments and observations. Understanding time's relative nature opens doors to a deeper appreciation of our universe. Next, we'll explore how motion influences time dilation further. In this segment, we unravel one of the most intriguing aspects of Einstein's theory of relativity, time dilation. Simply put, time dilation is the effect where time passes at different rates for objects moving relative to one another. This phenomenon becomes noticeable at very high speeds, approaching the speed of light. Imagine you're on a spaceship traveling close to the speed of light. To an outside observer watching from Earth, time on board your spaceship would appear to slow down. Clocks on your spaceship would tick slower compared to those on Earth. This is because, according to relativity, motion affects how time is experienced. The faster you move through space, the slower you move through time, relative to a stationary observer. This isn't just a theoretical idea, it's a fundamental aspect of our universe. The concepts of time and space are intertwined, forming what we call spacetime. When we move quickly through space, our movement through time is altered as well. Understanding this can be quite complex, but it has profound implications for our grasp of reality. The faster an object moves, the more significant the time dilation effect becomes. We'll explore how gravity also plays a crucial role in affecting time. Stay tuned to see how these mind-bending concepts shape our understanding of the universe. Welcome back as we delve deeper into the fascinating world of time dilation. We've seen how motion affects time, causing it to slow down as objects speed up. Did you know that gravity also has a profound effect on the passage of time? According to Einstein's general theory of relativity, the stronger the gravitational field, the slower time moves. This phenomenon is known as gravitational time dilation. Imagine being on an incredibly massive object like a black hole, where gravity is immensely strong. There, time ticks by much more slowly compared to someone far away from such a gravitational field. To put it simply, gravity warps the fabric of space-time, causing clocks to run slower closer to massive objects. For instance, if you were to spend time near a supermassive black hole and then return to Earth, you would find that much more time has passed on Earth than it did for you near the black hole. This is not just a theoretical concept, it's a real effect that has been observed and measured. Intriguingly, astronauts aboard the International Space Station actually age a bit slower than we do on Earth because they are farther from Earth's gravitational pull. Understanding this concept helps explain some of the most mysterious phenomena in the universe and sheds light on how interconnected space and time truly are. We'll explore how these principles have practical implications in everyday technologies. Stay tuned. Time dilation isn't just a theory confined to the pages of a physics textbook. It has tangible effects that we can observe in the real world. Let's start with GPS satellites. These high-flying navigators orbit the Earth at tremendous speeds and at altitudes where gravitational effects differ significantly from those on the ground. To ensure that the GPS signals remain accurate, scientists must account for both the effects of their velocity and the difference in gravitational pull. Without these adjustments, your GPS readings could be off by several miles each day. Now, consider astronauts aboard the International Space Station. Traveling at approximately 17,500 miles per hour, they experience time just a little bit more slowly compared to us on Earth. This effect is minuscule but measurable. If an astronaut stayed in orbit for 6 months, they would have aged just a tiny fraction of a second less than their friends and family on Earth. These examples show that time dilation is all around us, influencing everyday technology and space travel. It's a vivid reminder of how interconnected and dynamic our universe truly is. You'll see more intriguing scenarios where time dilation plays a crucial role, including thought experiments and even science fiction portrayals. Stay tuned. The twin paradox is a thought experiment that vividly illustrates the effects of time dilation. Imagine identical twins, one stays on Earth, while the other embarks on a high-speed journey through space. As the traveling twin speeds through the cosmos, time slows down for them compared to their sibling on Earth. Upon returning, the spacefaring twin finds that less time has passed for them than for their Earthbound counterpart, who has aged more. This paradox, grounded in the theory of relativity, not only defies our intuitive sense of time but also highlights profound implications for our understanding of reality. Time, it turns out, is not a fixed entity. It bends and stretches based on motion. These nuances reshape our perception of the universe. Stay with us as we continue to unravel the mysteries of time and see how these concepts impact both science fiction and real-world applications. Science fiction often explores the concept of time dilation, making it a popular theme in movies and books. From the slow-motion sequences in Interstellar to the time-warping adventures in Doctor Who. These stories captivate our imagination with the possibilities of time travel and manipulation. In 2001, A Space Odyssey, time dilation is hinted at subtly, while in The Forever War, it becomes a central plot device that underscores the emotional impact of elapsed time on human relationships. By incorporating time dilation, these narratives not only entertain but also provide thought-provoking perspectives on our understanding of time. Science fiction allows creative interpretations of this complex phenomenon. We'll delve deeper into the math and experimental evidence behind time dilation, grounding these imaginative tales in scientific reality. Up next, we will explore the mathematics that underpin time dilation and unveil how Einstein's brilliant equations come into play. Let's dive into the mathematics of time dilation and see how we can calculate it. At its core, time dilation is described by Einstein's theory of relativity. We can quantify this fascinating concept using a fundamental equation. It begins with the Lorentz factor, represented by the Greek letter gamma. Gamma equals 1 over the square root of 1 minus the velocity squared divided by the speed of light squared. As an object moves closer to the speed of light, gamma increases significantly. This increase in gamma directly affects the passage of time. For an observer moving close to light speed, time appears to slow down compared to someone stationary. We express this mathematically using the equation, delta t prime equals delta t times gamma. Here, delta t prime is the time interval observed by the moving observer, delta t is the time interval for the stationary observer, and gamma is our Lorentz factor. By plugging in the values, we can calculate the observed time dilation. For instance, if an astronaut travels at 99% of the speed of light, gamma becomes approximately 7. This means time for the astronaut slows down by a factor of 7. What seems like an hour for them could be 7 hours for someone on Earth. These calculations reveal how profoundly motion affects time. Now that we've laid the mathematical groundwork, we'll explore experimental evidence that confirms time dilation in practical scenarios. Numerous experiments have confirmed the astonishing reality of time dilation. One of the most notable is the Haffel-Keating experiment. In 1971, scientists placed atomic clocks on commercial airliners and flew them around the world. Upon their return, the clocks showed a slight discrepancy compared to those that remained on the ground. This phenomenon wasn't just a fluke, it was strong empirical evidence for time dilation, as predicted by Einstein's theory of relativity. These results have been replicated in various forms, each providing further proof that time dilation isn't merely a theoretical concept, it's measurable reality. These experiments shape our understanding of the universe and pave the way for future discoveries. Time dilation presents profound implications for the future of space travel, significantly impacting long-duration missions. Imagine astronauts embarking on a journey to distant stars at near-light speeds. Time, for them, would slow dramatically compared to those remaining on Earth. This means that what may appear as years to the travelers might translate to decades or even centuries at home. As we venture further into the cosmos, these effects become increasingly critical. Engineers and mission planners must account for time disparities when designing spacecraft and coordinating communication across vast distances. Understanding time dilation reshapes our approach to exploration and influences how we envision our place in the universe. Innovations in propulsion systems and journey logistics will need to adapt to these relativistic phenomena. We'll explore how these scientific principles are paving the way for our future in space. Time dilation challenges our fundamental understanding of time, posing profound philosophical questions. How do we reconcile our everyday experience of time with a reality where time can stretch and compress based on motion and gravity? This revelation forces us to rethink concepts we take for granted, like the flow of time and the nature of reality. For centuries, philosophers and scientists debated the nature of time, and now, with the evidence of time dilation, their questions have gained new dimensions. How does time dilation affect our understanding of cause and effect, of past, present, and future? These questions don't just push the boundaries of science, they also invite us to deeply reflect on our place in the universe. As we delve deeper, you'll see how these philosophical questions connect with scientific evidence and influence our daily lives. Let's address some common misconceptions about time dilation and clarify any misunderstandings. Many believe that time dilation is purely hypothetical, but it's a well-documented phenomenon with real-world implications. For instance, a common myth is that time dilation is only relevant at speeds close to light. In reality, Even astronauts in space experience time differently due to both their motion and gravity's influence. Another misconception is that time dilation means slowing down one's perception of time. Rather, it's the actual physical passage of time that changes. These subtleties highlight why time dilation is such a remarkable concept, challenging our everyday understanding of time and space. You'll see how this phenomenon plays out in various contexts, shedding light on its true significance. As we conclude, let's briefly recap the main ideas we've explored. Time dilation is a profound concept, highlighting that time is not absolute but relative. Both motion and gravity play critical roles in altering the pace at which time flows. We've delved into how high-speed travel can slow down time, and how intense gravitational fields, like those near a black hole, can produce similar effects. By understanding these principles, we gain deeper insights into the nature of our universe. Grasping time dilation's intricacies not only enriches our knowledge of physics but also opens up possibilities for future technological advancements. Remember that time dilation, with its many layers, invites us to keep questioning and exploring beyond our everyday experiences. If you've found our journey through the science of time dilation intriguing, there's much more to explore. Make sure to hit that subscribe button for more fascinating content on science and physics. Share this video with your friends, so they can join in on the excitement too. Every share helps our community of curious minds grow. Stay curious, keep learning, and let's uncover the wonders of the universe together. Thank you for watching, and we'll see you in the next video.